Okay, so we are going to talk about polarimetric basics. So I will just go through some definitions. We'll start from a definition of what is the polarization of a wave, and we will see how we can measure this information using a radar. And we will also provide what is interesting in polarimetry, the interpretation you make of polarimetric parameters in terms of geophysical properties of the objects you are looking at. This is the objective. So first, I would like to acknowledge my co-author, Eric Potier, who is with the University of Rennes. Rennes is in the northwest part of France, close to facing England. And we've been working, as I told you yesterday, for more than 25 years together. And he was the one who designed PolSAR Pro. PolSAR Pro was the ancestor of the program you saw yesterday. It is still a complete toolbox made of C programs and TCL-TK interface. And it contains a wide variety of procedures. Eric, we started coding this toolbox together, but after Eric went on programming, and he included a lot of contributions from the community. And I think this toolbox made the community stay together. You know, young people were interested into proposing their new algorithm, and Eric was organizing the whole software so that, you know, if you want a specific polarimetric decomposition, you can program it yourself from the paper. Sometimes papers are not that obvious to understand when you don't know them, or it takes some time and you don't know if this will be useful for you. I would recommend you to download the PolSAR Pro, install it, and just run it on your favorite data. It is easy to use. It is meant to be easy to use, and there are loads of tutorials on the internet, and you will be able to appreciate Eric has a French accent even stronger than mine, so it's very funny when you hear him talking in English. Radar. Okay, this lecture has the objective to provide you the minimum amount of knowledge, of information to understand the presentation. I don't know if you will attend the workshop next week, but after the lecture you have this week, you will be able to attend and to understand what's going on when you see the presentation. Otherwise, you will not have a clue. You know, people will talk about the compositions, about interferometry, about combining both modes. And it can become quite complex. And after this week, you will be, maybe you will not understand all the details, but you will be able to follow the arguments and to understand why people exchange and why they agree or not on some points. And of course, the very basics I'm going to present are the basic tools or the basic bricks you need to assimilate in order to know why people prefer to perform SAR tomography at HH rather than VV or rather than HV, and what you can see in depending on the polarization. So it's important. So a general introduction. So radar polarimetry, polar means polarization, metry means measurement. Okay, it is the science, as this has been written by Eric, of acquiring, processing, and analyzing the polarization state of a wave. So this is we are going to understand what this means, but this is what we use to explain what polarization is for a wave. So it has to do with basic properties of propagating fields, electromagnetic fields. And of course, this technique is used to infer or to guess some geophysical properties of environments we are looking at, like a mountain. We want to guess some of their basic electromagnetic properties. So in this way, radar polarimetry is a huge simplification of electromagnetic modeling. When you want to model the response of an environment, you need tens, hundreds, thousands of parameters. And with polarimetry, you try to guess 2, 3, 4, to guess some properties you are interested in. Okay. In this way, in this sense, the experience and you have with manipulating polarimetry concept is very important. So it has been applied to many different kinds of environments. Back in the very old times, when I started my PhD, many people were working with single polarization images because this is what we had, with ERS, we had intensities with very coarse resolution. And from only the backscattered intensity, they tried to guess some properties like soil moisture, like biomass, or the density of built-up areas. And this, of course, it's a very ill-conditioned inverse problem. So for one value of intensity, you have many different configurations which give the same backscattering. And in this way, polarization, you will see, opens the possibilities and increase the dimension of the observation space. So it has been used in different kind of applications. Here, there are 4 fields that are represented, but you can find, if you go through the proceedings of the different editions of the PolSAR conference, you will see many applications. One of them was monitoring oyster farms in Malaysia. Some very exotic applications you will never guess when you work with polarization. Some friends work on sea ice classification. It's a classic of polarimetric application. You can monitor forests. You can guess the orientation of objects. When you monitor constructions, etc., etc. Okay, some sensors that used to some of them had a polarimetric diversity. ERS was only using a VV polarization, and as mentioned yesterday, Francesco, there was the development of SAR polarimetry using spaceborne sensors got a big impulse, a big step forward when we could work with the results of the CERC campaign, which was conducted in '94 by the ESA JPR, and they could deliver for free some information to the whole planet. But all the sensors I mentioned here are characterized by the fact that they use a single polarization. We will see what a polarization is, but they work according to the following principle. They transmit, and receive through the same antenna. So they, or similar antennas. Then they transmit one pulse, receive one pulse, and each of these pulses have been measured by an antenna with the same polarization. So this is called a scalar acquisition. So this is a comparison of an optical image, and of a classical intensity image. I like to represent images with a grayscale. I've been used to it. Today the tendency is to use color scale, but it's hard to analyze. With grayscale, this is the Bay of San Francisco. You will be working on this image this afternoon in the practical. Back in the late 90s, there were very few polarimetric SAR images you could use, and San Francisco was one of them. It was very famous. So I've never been to San Francisco, but I know very well the city. I know the stadiums. I know the different areas, the Golden Gate Bridge, etc., etc. The currents. So this is an optical image, and the SAR image, you see there is the correspondence is very strange between a SAR image and an optical one. Here, this looks very homogeneous, and here we see some variations. These are due to the currents and also to the sea state. Sometimes you have winds coming from different directions, and the sea surface is very slick. And when it is slick, the sensors, the wave that are emitted by the sensors are scattered away in the other direction, and you have a very low intensity. Here in this area, the brightest points correspond to highly to dense urban environments in this region. And you have also some natural environments with some parks and some golf courses. And if you want to analyze this image, of course, if you want to analyze the sea surface SAR information is very useful, but if you want really to understand what's going on, an optical image is preferable. And of course, you can make this observation at different polarization. And when you switch from one to the other, you look, there is a difference, Basically, for those of you who have never worked on antenna design, a horizontal antenna is a horizontal dipole. So you take a wire, and if it is aligned with the horizontal direction, it emits a horizontally polarized wave. And then if you rotate it, then you go to vertical polarization. And what you see is that this, yes, like this. You see there are some changes from one polarization to the other. And so if you want to measure polarimetric information, then you will need a second antenna. You will need to emit a pulse on a polarization, let's say X, which will be horizontal, and you can measure both with X and Y, measure with two antennas, and then you have an enhanced polarimetric information, and you can measure vectors. Okay. And when you measure vectors, then you can simultaneously compare two polarization channels. And then you see, when you compare HH and HV, I know why these images are different. You still don't know. At the end of the lecture, you will know why they differ. Okay, this is the objective of what we are going to present today. But basically, the difference between HV and HH is extremely important compared to the difference between HH and VV. Okay, this is called a copol because we use the same polarization when we emit and we receive. And here we use orthogonal polarization, or horizontal and vertical one. And the difference is extremely high. And then some sensors have this capability to measure dual polarization information, like the Cosmos Chimed and the Terrasar X, etc., etc. This RISAT by the Indian Space Agency. Sentinel-1 is a dual polarization system, and they choose VV and they call it VH, but in fact we will see that it should be called HV. Now it's on all the websites, so it's wrong. There's nothing bad with this, but it should be called, you will see logically it should be called HV. Okay, and then you get what you will learn also to do during this afternoon. You can combine information measured on different polarization channels and combine them into a color-coded image, and it is very nice. And it's nice looking. It looks nice, but it's nice also because you can give a very fast interpretation of what's going on. You know, when you are used to a specific color coding, you say, "Oh, this is a building, this is a forest, this is surface." It's very fast. And there are also some some sensors that measure what we call the full polarimetric response of environments. Okay, so we emitted horizontal, received horizontal. After we emitted horizontal and we received vertical, and now we're using a switch. We can emit at both horizontal and vertical polarizations, and of course we receive along these two channels. And then we don't measure a vector now, we measure a matrix, okay, a 2x2 matrix, which corresponds to the emitted and received information. And in this case, of course, you can play with four coefficients. We will see that in classical configuration, these two coefficients should be equal. Okay. And then, in fact, you have three coefficients, and then you can simultaneously compare their amplitude, their phase, and play with this in order to detect some specific properties. And you have this very nice looking images. Okay, this is a so-called lexicographic color-coded image, where you have everywhere. When you have a pink color, it means that HH and VV are very strong, typical of surface. And the surface scattering, HV, strong green component means a lot of volume scattering, etc., etc. And you can also play with them. And for instance, we will see that HH plus VV is an indicator of scattering by a surface, whereas HH minus VV is typical of double band scattering. You know, the wave undergoes two bounces before going back to the radar. And you have this very famous, you will do it this afternoon, this very famous color-coded image where they choose correctly the colors so that the sea was looking blue. This is not has nothing to do with world physics, it's just a choice, but a good choice. And you have, of course, as said Francesco yesterday, the SAR mission launched in '94 was a great provider of polarimetric images all over the world. The ESA did it and they distributed the data to everybody. And it was, they were right to do it because suddenly there are lots of contributions by scientists who try to analyze these very nice looking images. But because when you look at this volcano, okay, this is a volcano in Rwanda, you see some uniform features, but you see something which looks like specific lava flows with a color, and obviously there is a different kind of scattering occurring within these flows. And from people who are working on geology, geophysics, this is important. I know there are still some studies at the moment dealing with the characterization of volcanic areas and which use polarimetric diversity. ALOS PolSAR is this Japanese satellite, and it provides also sometimes fully polarimetric information. And there are all kinds of sensors, okay, Chinese ones, of course, and European ones, were the ones managed by the Italian Space Agency, Cosmos SkyMed at X-band, and the upcoming biomass sensor, which will be fully polarimetric, because this, for many reasons, because its polarization is good for analyzing environment, but also because at this frequency, at lower frequencies, the propagation through the atmosphere is really not simple. There are some rotations occurring, and if you want to compensate this rotation, you need to acquire the whole scattering matrix. And with the dual polarization, it's very hard to do it correctly, and this is why they went for a fully polarimetric acquisition. TandemL, which is there are some projects like this. People have been talking for 15 years, but still not planned. And because it's a very nice project, but I don't know why it is not not funded at the moment. TandemL is, I don't know if you're familiar with TandemX. TandemX, there is a TerraSAR X, which flies at X-band. TandemX is a set of two satellites, and they do single pass interferometry, so without temporal decorrelation. And the idea would be to do the same at L-band. And we are sure this would give fantastic results. Just need to find money. Okay. I will let you for your curiosity. Of course, all these specificities in this processing have been that you can find in the literature. Many of them have been integrated in PolSAR Pro, which in the years became PolSAR Pro Bio, okay, like biomass. And there are many contributions from different colleagues, such as Carlos and others, and all the colleagues you will see this week contributed to this toolbox. Okay, and there are some books. One of them has been written by Yongsen Lee from the Lee filter himself and Eric, and another one by Shane Cloud. And you will see today that the cloud Poitier decomposition is maybe the most famous one. So these are good references. Okay, now let's go to. Don't worry, I don't remember what these equations mean. Just we showed them to show that we start from the basics. So these are the relationship between the electrical and magnetic fields of a wave, of electromagnetic wave, and from these relationships, and in simple conditions in the vacuum, you have a wave which propagates, satisfies this kind of equation, okay? And when there are no free charges in the medium, they simplify to this equation that many of you may know. If you don't know it, don't worry. You don't really need this to understand polarization, but this is the solution of the propagation of waves inside the vacuum. And when you consider monochromatic waves means single frequency, one color, single frequency. So when you emit, let's say, at around at L bands with a signal whose frequency, whose bandwidth is narrow enough, we can consider it as a quasi-monochromatic. And the solution of the wave propagation, one of the solutions is this one, okay, where we have a field which propagates, in this case, along the Z direction. Why Z? Because it's an arbitrary choice. Okay, we took this way of representing the different components. And if we align one axis with the propagation direction of the wave, we have 1, 0 in this vector. So it's a good choice. And here you see, for those of you who don't know what propagation means, you have a sine function here, which is a function of space and time. Okay, space is represented by Z, the position you propagate along the position along the propagation direction, and T, the time you are considering. So if you fix, let us fix the time. You will have a cosine like this blue cosine, okay, which has a given shape. And as time goes, okay, you are going to shift to slightly delay this wave, and this is why it will slide along its propagation axis. Okay, as you can observe, this wave here has two components, which are representing into a Cartesian coordinate system, X and Y. X represent a horizontal axis, and Y represent the vertical axis. If you take a non-remarkable polarization state, okay, you will have the electromagnetic field, okay, the extremity of the electromagnetic field will describe what we call a locus, which is represented here in rain, like a corkscrew, the one you use to open wine bottles. And it's not easy to analyze, okay, because it has a 3D shape and it rotates. And in fact, if you decompose this red curve, 3D curve, onto the YZ plane and the XZ plane, you get the two green and blue components, which are much easier to understand. Okay, these two components are characterized by, of course, an angular frequency. They all have the same. A wave number, they all have the same. And in fact, these two components have specific terms that are an amplitude, which can be different. Okay, you can have waves with a small amplitude in the vertical direction, a large one, and this phase shift. The phase difference, it plays an important role in SAR polarimetry. Okay. Depending on the phase shift, you can go from this corkscrew-like trajectory can describe an ellipse, okay, or can describe a circle or a line. Okay, so when the electromagnetic field propagates, it moves, it moves like this, really. And if you put a vertical plane, which is orthogonal to the propagation of direction, to the direction of propagation, sorry, and you let the electromagnetic field go through this plane, then you will see that as time goes, it describes a polarization ellipse. Okay, and this ellipse is all what you need to know if you want to define the polarization of the wave. Why? Because it is for a single position. So if we go back to the complicated expressions here, you have time, space, and two coefficients. If you set the plane at a given a position and you let time go, then you can remove these two components. You remove the time and the space components of your expression, and then you concentrate on two coefficients for each axis, the amplitude and the phase shift. Okay. And this ellipse is defined by a very small number of coefficients, which are the two amplitudes and the phase difference. And depending on the electromagnetic field, you will see that this ellipse takes some different shapes. And this is a very easy way to represent polarization. This was not invented by radar engineers. This is what they do. They've been doing for a long time in optics. How to define a polarization ellipse? There are many definitions. Of course, one it's a bit like phase unwrapping. At the end, everybody used the same solution, luckily. So today, the polarization ellipse is defined by a set of 4 parameters, which are the wave amplitude. Okay, the wave amplitude is not the length of the major axis, it is the length of this axis here. Okay, so the wider, when you have a large A value, it means that you have a large amplitude of the electromagnetic field, and the opposite. The phi here represents the orientation of the ellipse with respect to the propagation axis. Okay, so if we go here, the phi would be the orientation of this axis here with respect to x. This parameter is defined between -π/2 and +π/2. Okay, why? Because if you have an orientation which is larger than π/2, then you're ambiguous. Okay. And one of the very important parameters of the polarization of the description is the ellipticity angle, which is the angle between the major axis of the ellipse and this segment here. Okay, and when tau is equal to 0, okay, the ellipse collapses to a line. Okay, it becomes a line. And when tau reaches its maximum value, which is π/4, then the ellipse becomes a circle. And why cannot it be larger than π/4? Because if it becomes larger than π/4, it means that this axis will be larger than this one. And then we just change the definition. Okay? We just change the value of phi, and then we get back to a small value of tau, which is smaller than π/4. Okay? So we have and the absolute phase is the location of the electric field for time t equals 0. Okay, it's a function of the position, and this is what we use to perform interferometry, for instance. Okay, but for polarimetric studies, we don't care about this parameter. We just get rid of it. Okay. One thing which you cannot see on my slide here is that here, this is not meant to be a. I don't have a pen here. It's not meant to be a square. It should be, one circle with a dot inside, showing that in this case the z-axis is meant to get out of the screen. Okay, the polarization ellipse is defined when you look. Okay, we will see it later. But when you look at a wave from a given position. So you put yourself, if you want to define the, okay, we say that as time goes, you have the electric field, okay, rotates, okay, and describes the polarization ellipse. And of course, when you rotate, you can rotate one way or the other, okay. And these two overpolarization states, they can be orthogonal. So it's very important to know which way the field rotates. There is a short story about this during one of the first transmissions over the Atlantic Ocean. There were some were using some very first experiments of radio communications. They were using circularly polarized waves. And of course, they did not agree on the way to representing this, on the way for representing the sense of rotation of the wave. And of course, two groups make an experiment, and one of them could receive the wave, could receive the signal, and the other not, because they were using simply an orthogonal polarization state. Okay, so it's very important to know in which sense the wave rotates. And we design. There has been a convention which has been established by the IEEE normalizing group, and they say that the sense of rotation is assigned to tau, to the value of tau, which is you define. If you want to define in which sense a wave rotates, you just need to let the wave go. It propagates into this direction. You put yourself behind the wave. This is what is meant here with the eye. Now you have the eye on the left. So you are behind the wave. You look at it while it goes, and then when a wave rotates this way, it's called right-handed polarization, okay? And in this way, it's called left-handed polarization. Okay? They had to decide something, they decided this way. So it's a convention, we just need to accept it, okay? So a wave rotating like this, it would be right-handed polarization, okay? And the one rotating like this would be a left-handed, okay? So when it is clockwise, it's right-handed. And of course, they assign to tau, and they say tau will be negative for right-handed polarization, and this is completely arbitrary. Okay. So now we know that if we want to represent the ellipse, we just need a set of parameters, which is the ones that is mentioned here. So it means that we can reduce this this complex expression of that you can find everywhere of a plane of a propagating plane wave. We can just get rid of this information here, which does not describe the polarization, but describe the phase of the or the amplitude and the instantaneous amplitude and phase of the wave as it propagates. You just want to concentrate on what is called the complex envelope of the wave. And it is a phasor. It is a complex vector with two amplitudes corresponding to the amplitude of the field according to the x and y axis and to their phase. And we know that their phase are defined by an absolute value, alpha, and a difference, which is what we are using to analyze the polarization state. Okay, so on this slide, the absolute phase is delta x, and delta means the difference between the where is this difference between the two phases. Okay. And of course, if you want to make calculations, you can define all the parameters, the orientation and the ellipticity, etc., as a function of these two parameters. Okay, some examples. If you have a horizontal linear polarization, okay, which is characterized by a so-called Jones vector, which has a component of 1 in the x means horizontal, 1 in the x component and 0 on the vertical one, okay? This corresponds, in fact, to an orientation of 0, okay? And to a value of ellipticity of 0, 2, okay? So if I go here, a horizontal is like it is this ellipse, but which becomes completely flat. So the aperture will be 0, and the orientation with respect to the horizontal axis will be 0, 2. Vertical polarization, we have the opposite in terms of Jones vector, 0, 1. Okay, it's still a flat ellipse, but it is oriented. It has an orientation of pi over 2, and then you have the left circular ellipse and the right circular one. Okay, right. So it means that we are looking this way, and for these two polarizations, circular ellipses are circular polarization are characterized by a value of tau which is equal to plus plus or minus pi divided by 4. And in this case, the orientation is meaningless. So it is something you don't care. Any value is okay. And in polarimetric processing, we like to deal with matrices because they are easy to manipulate. Okay, and we are electrical engineers, most of us. So we like this way of representing the information. And people found out that they could represent a polarization, an arbitrary polarization state using a set of matrices, okay, which correspond to a rotation. This is typically a rotation. This is a rotation in the complex plane, and these are phase shifts, okay? And they say that any polarization can be a Jones vector corresponding to a horizontal wave, okay, multiplied by a set of 3 transformations. Why are we doing this? Because this is how they represent polarization in optics. You know, they set for polarization state, and they put one lens or one polarizer and one devices, and they transform step by step the polarization of the waves. And we can do it exactly the same way. Now we have vectors, Jones vectors. They are complex valued vectors, okay? Why complex? Because we have these two components, the ellipticity and the phase shift. And of course, we can define an algebra from these vectors. We can make a scalar product, which will be a Hermitian product. We can look for orthogonality between them. We can compute norms, etc., etc. Okay. We are going very quickly over this because it's a bit boring for you if we present this only in 1 hour. But when I was a student, we spent hours on manipulating these matrices, inverting, etc., looking for trying to guess the best parameter combination in order to reveal one geophysical property. So we can define, if you can define a Jones vector from the horizontal one using a specific polarimetric transformation, then you can define its orthogonal. I'm sorry, in the final version of the slides, you will have a, here I realized that some signs cannot be seen here. This is an orthogonal polarization state, okay? You can define it by applying exactly the same transformation to a vector which is vertical instead of horizontal, okay? And then these two, sorry, again, this is E and E orthogonal. You can obtain them from the same transformation, but just by changing the original basis, okay? And this is what brings us to the famous concept of change of polarimetric basis. Once you acquired a polarimetric information into a specific basis, let's say horizontal, vertical, you can transform this signal into any arbitrary polarization basis using some matrix manipulations, okay? It is very easy to do. If you don't know how to do it, you just download PolSAR Pro and you can do it. You just need to select the values of the parameters, and then you have, the objective is that you, of this transformation is to find the polarization state, or maybe the transformation which best fits your application. You know, if you want to reveal a specific state of a forest or specific kind of agricultural behavior or I don't know, of drought state or whatever, you may wish to fit the polarization of you are using to better detect this, and this can be done using this very simple matrix multiplications. Again, compared to what our colleagues do when they study wave propagation and electromagnetic, this is a very, very simplified description. We just use a plane wave and very simple transformations. How do you define two orthogonal waves? Okay, the condition to have an orthogonal basis is that you use two orthogonal polarization states, and it's easy. You just take the phi and tau parameters of this ellipse, okay, and you apply you transform phi. You apply pi over 2 to phi, and you transform tau to minus tau. Okay, so and this is over for the theoretical part of my speech. Now we are going to see how you can use this when you are dealing with SAR images. So how to measure polarization? Now you know you need two antennas whose polarization stats are not parallel, okay? And if you want to have a good isolation, then you are looking for orthogonal polarization states, okay? When you design a SAR device, a polarimetric one, the so-called polarimetric isolation is a key parameter. Some people, depending on the applications, if you want to detect, for instance, boats over sea, you will use HV to do it. You saw it before over the flat sea, HV reflectivity is very low. And when you have a boat, it becomes much larger. So it's an easy way to detect ships. But if you want to do it, you need to have a good isolation between your antennas. You need to be sure that they measure what they are supposed to measure, okay? And they don't transform the polarization. So if you want to measure the Jones vectors, you will just need to use two antennas, one to transmit waves, okay, and receive waves, and the other one just as a receiver, okay? And in this way, you transmit X and you receive X and Y. Okay. So this is why when you look at it, okay. I will come back to the Sentinel-1 notation later. So this is the way you have to do if you want to measure Jones vectors. Let's say now you want to measure the Jones vector when you emit H polarization, which is this vector, and the same measurement can be done when you transmit a vertically polarized wave, and then you measure this Jones vector. And if you put them together, you have a matrix. Okay. Okay, and from this matrix, you can, when you have the matrix, if you multiply here by 0, 1, you will get the measurements when you transmitted the vertical polarization. And if you multiply by 1, 0, you will get only this column, which corresponds to the measurement when you transmitted only H polarized waves. And so what does Sentinel-1 measure? Sentinel-1 measures this vector here. It transmits V and receives H and V, okay? And if you read well, this corresponds to VV and HV, not VH, okay? Because VH means that if you measure VV and VH, means that you transmit V and H and you measure only V, okay? It's not the same. And this has nothing to do with convention. It's just that it's a matrix representation, something simple. What radar polarimetry don't say when they present, generally don't say when they present this basic behavior of sequence of SAR acquisition in polarimetric mode, is that measuring polarization has a price. It has a price. You always need to pay a price in physics. So if you want more information about polarization, then if you do this kind of acquisition here, you just need to pay a bit more, because instead of having one receiving channel in X, when you emit in a horizontally polarized wave, you need to have a receiving channel in the H polarization. You need to double your receiving channels to measure also the V channel at the same time. So it means a bit more, a little more money. Money can be not so problematic, because it is not that expensive. But when you measure the complete scattering matrix, there is a physical problem in addition. You see that you need to transmit H and V polarized wave. And you need to do it twice faster. Okay, if you compare this acquisition here and this one, you see that in the same period, you need to transmit 2 pulses. Okay, and this is a big problem for synthetic aperture radar devices, because the way the cadence of transmission of pulses depend on your antenna aperture. You need to respect the theorem of Shannon-Nyquist. You need to sample the signal correctly, and if you sample, if you take more time between 2 samples here, it means that you will measure a signal with a narrower antenna. Okay, narrower antenna means coarser resolution. It means also in range, you will have a problem of ambiguity. So this is why when you look at the products proposed by all the space agencies in the polarimetric mode, normally the swath is smaller, okay, and much smaller, okay. And this is a problem. Now people like to have a huge SAR images like the one proposed by Sentinel-1, okay, with they use a scant SAR mode. And this mode is, when you use polarization, of course, you reduce the swath, which goes against this wide area coverage capability. Okay, so it's a choice. It's a choice you need to do. This is why more and more sensors concentrate on this kind of solution, okay? Because then they don't need to reduce the to increase the pulse repeat frequency. Okay, so now we are going to see some different representations. I thought I would be fast, but I will not be that fast. Generally used, okay, it's a question of vocabulary. There are many arbitrary definitions, but you need to know them, otherwise you will not understand people who talk about this when you attend the conference. So this S matrix is called the scattering matrix, but it is also called the Sinclair matrix because there was in the 40s and after well-known scientists working on polarization, and his name was Sinclair. And Keno also was a very famous scientist working on the study of polarization. The nice thing with polarimetry is that you still can read some papers of it is a very recent development, so you can meet some people who wrote a historical paper. Okay, so we are dealing now with our scattering matrix, which is composed of, it has 4 coefficients here. What I forgot to mention here in this acquisition, on this slide, is that when the antennas, the transmitting and receiving antennas, or the H and V, are co-localized or they are very close one to the other, the antenna theory shows us that these 2 coefficients here should be equal. If they are not equal, this is because the acquisition noise is not the same, but the physics tells us that transmitting a H and receiving a V wave is exactly like transmitting a V wave and receiving H. Okay. There's no difference. So this is why you will see from now on in this presentation, scattering matrix having a symmetric property. Okay, this coefficient here is equal to this one. When you are using bistatic system, this is not true anymore, not at all. And this is one of the richness of future bistatic system. They will measure polarimetric information that we don't know today, because all the system today bring the antennas on the satellites, and the distance between antennas is maybe 1 or 2 meters. And when you measure at 800 kilometers from the Earth, you can consider that they are exactly located at the same place. Okay. But if you plan to use bistatic system with wide bistatic angles, okay, you have one transmitter here and a receiver, or another system with another polarization located at a large distance, then this property will not be verified anymore, and we will have a 1 more degree of freedom if we want to play with polarization. Okay, so we have 3 coefficients, complex coefficients. We can say 3 moduli, the modulus of this one, and this one, and 3 phases. Okay, we know that we don't want to we are not interested in absolute phases. We don't want to do interferometry. We just want to study the phase difference between the channels. This is why normally we factorize, no, not normally, we factorize 1 phase term out of the 3, and it is normally the HH1, but there is no rule. Okay, you can do what you want. And at the end, what we get, we can describe this matrix here with 5 parameters: this amplitude, this amplitude, this amplitude, and these 2 phase differences. So it means 5 coefficients. So this is the limit of what we can retrieve with one single Sinclair matrix. Okay, you will have, if you manage to relate this coefficient using a simple model to geophysical properties, you cannot address more than 5 properties or retrieve more than 5 properties. And if you know a bit of physics, you know it will be less than 5. Okay, so some images of this is a very old image. It was, I think, 1988 SAR image of San Francisco Bay. With here, let me describe this image. Here you have the sea, here you have a lighthouse, the Golden Gate Bridge, here the prison of Alcatraz, here you have some built-up areas. This is a Golden Gate Park, golf course, and some other areas with a slight topography. You see these undulations of reflectivity. Here is due to the topography of the city. So here you have the Eric made an error. This is his slide. Okay, here on this image you transmit H and you receive H. Okay, on this image, if you write HV, it means you transmit V and you receive H, not the opposite. Okay, but we know now these two coefficients are the same. Okay, so we will not comment this anymore. And this is what you measure when you transmit V and you receive V. It is well known that over surfaces, rough surfaces, VV is larger than HH. All the scattering models use this property. Okay. And for the story, we have last year I had the chance to make a cruise on an Arctic boat to measure sea ice. And there are some wide areas in the Arctic where it looks like a surface, like a nice surface, and we observe that HH is larger than VV, and we still don't know why. We're still looking. It's hard to explain because you cannot go very often there to make some samples and to measure what's going on. But there are some hypotheses, but we don't really know what's going on. So the surface is VV is larger than HH. And of course, if you combine all these images into a color composition, which is completely arbitrary, but you can choose the colors so that they look nice, you get this image, which now gets the ability or gives you some possibilities for interpretation. In green, you have it's obvious that you are measuring the presence of vegetation or of volumetric scattering. And in pink color, you are measuring the presence of HH and VV. Okay. And of course, by changing the polarization basis, like I showed before, you can play, and depending on your color coding, you may enhance or not specific phenomena occurring over the scene. Okay, so how to change a polarization basis? You know, if I may go back to what we said before. Here we showed that how we could change from one Jones vector to the other using a specific 2x2 matrix, okay, which is built by from the coefficient of the polarization ellipse. And if you remember that the scattering matrix is composed of two Jones vectors here, they can both be transformed, and you can do it very easily using the same kind of 2x2 matrix. Okay. If you measure scattering matrix in the HV basis, you can represent it into the circular basis with a simple transformation, just a question of coefficient. Okay, so here is the color coding in the most used basis, which is called the Pauli basis, from the very famous Pauli, the physicist. No, I never know. Physicist, yeah, a very famous physicist. And because these transformation matrices can be expressed in terms of spinors. If you want to make things complex, you can with polarization. But if you want to keep things simple, you just take these matrices as they are. They are only simple transformations. And then you can have a very direct interpretation. Blue means single band scattering by rough surfaces. Red means double band scattering. We will see why very, very soon. And HV means that you have something which is depolarized. And what depolarized is normally at L band. This is volumetric environments such as small forest, trees, and agricultural fields. For the story, for the small story here, if I may zoom. Here, this is the Golden Gate Bridge, and when they first look at the images, you know, people were doing only polarimetry and not radar. So, oh, what is this? Are there boats, you know, boats standing on the side of the bridge? And in fact, no, these are not boats. You know, SAR is a question you measure. With SAR, you measure a phase difference. What Stefano said yesterday, when you move, a phase difference indicates you the position. The variation of phase indicates you the position. And when you are on the bridge, on this bridge, there are cars moving, okay, and their phase variation did not correspond to the one of a static target. And because of this phase variation, there is Doppler effect, and their response is completely shifted inside the water. This is hard to see when you're looking at only at a single polarization images with a fully polarimetric acquisition. It's obvious you detect them very well. It's very easy to detect. You will see with Armando Marino on Friday how he can detect ships with polarimetric data. It's fascinating. It works very, very well. Okay, this one. Why? Because as you can see, sorry. As you can see, it here C has most of the time is a kind of quite homogeneous background with a well polarized return. Okay, it's really like a surface. And when you put a ship on the sea, ships characterized by complex structures, you have metallic reflectors on a ship, and it's normally not polarimetric diversity is a good way to detect ships on sea. Okay, you can play with the polarization basis. Okay, now we are going to see target vectors, which are nothing special compared to matrix. You just change the way you represent the information. Okay, just a change of dimension. Okay, so we just take, you know, this 2x2 matrix here. This 2x2 matrix, and we say, okay, we have three coefficients, this one, and this one, which are really useful. This one is equal to the other, and we're just going to make a vector out of them, okay? Why this? Because we are paving the way to the covariance matrix concept. So we are moving slowly from the scattering matrix to target vectors. So once you have a target vector here, which is the HH, HV and square root of 2 HV. Why the square root of 2? Because if you compute the norm of this vector, you will have the norm of HH, norm VV, twice the norm of HV, okay? And it would be exactly equal to the norm of the scattering matrix. So you are conserving the intensity. And if you take this vector, you can, by just applying a linear combination, you can obtain an infinite number of transformed vectors. But among these infinite numbers is what is called the Pauli scattering vector, which considers HH plus VV, HH minus VV, and HV with this coefficient, so that both vectors have the same norm. Okay. In the polarimetric jargon, this is called a lexicographic vector, and this is called a Pauli vector. Again, a person name, but sorry for this. How to go from one to the other? It is just a linear transformation, which is invertible. So it means that these two representations are exactly equivalent. Okay, they're not equal, but are equivalent. You can go from one to the other and back when you want. Okay, and once you have a vector, what do we want to do when you study a little bit, when you remember what we did yesterday about speckle filtering? We want to compute second order statistics. When you do it with a single image, just take the square modulus and you make an averaging. When you have a multidimensional image, you compute the covariance matrix. Okay, and if you compute the covariance matrix of the Pauli vector, you will get a 3 by 3 covariance matrix, which is called the coherency matrix. And this matrix is can be parameterized in terms of coefficients A0, B0, B, etc. And this is represented here only because in the late 70s, this was the way to study polarization. There was John Heinen in his lab measuring targets in an anechoic chamber. I don't know if you know what an anechoic chamber is. It's like when people want to record music, they go into a studio, which is soundproof. And when you can have a room which are not soundproof, they are waveproof. There's some peaks going out of the walls, so that when you send a wave onto this wall, they can absorb it. Okay, and so it's a super quiet environment then. And Heinen were measuring the response of typical targets and trying to understand the relationship between polarization, the backscattered polarization, and the properties of the target. And it was a completely intuitive approach, not deductive approach, phenomenological one. And of course, it had his approach had its limits, but people showed after that he was in fact not wrong when he was providing interpretation in terms of these parameters. It's just that it was a bit old-fashioned. This was John Heinen, okay, and he defined it. He could associate some properties of the object he was measuring to some of these coefficients. Like this is a generator of target symmetry, non-symmetry, irregularity, and this is highly subjective. What is regular for you might not be regular for me, and okay. This is why after you will see with Carlos that people try to define to characterize polarization properties based on mathematical decompositions and interpretations that are more rigorous than this one or less subjective than this one. Okay, but what we can get out from all the work of Heinen is these very basic interpretations of a surface, a rough surface. Okay, electromagnetic models tell you that normally HH and VV have a almost zero phase difference. Okay, so they are in phase. So if you sum HH and VV, you will get a large number. Okay. On the opposite of a surface, if you make the difference between HH and VV, you should get a small number. And HV at order 1, okay, the HV of a surface is 0 at order 1. If you compute the higher order scattering response of HV, you will get something different from 1, but always very, very, very small, okay? So a surface is characterized by a in-phase HH and VV with normally comparable amplitudes. Of course, they are not exactly equal. They're not equal at all, but they are in phase. And the HV component is very small. Double band scattering is the scattering of the waves on the ground, on the wall, or on tree trunk, okay, when the wave interacts twice with an environment. This happens over, this effect is very, very strong over built-up environments and over forested. This is why we see the ground on tropical forests, we see the ground because due to this. Otherwise, the response of the ground could be very small compared to the one of the canopy. And in this case, when you experience double band scattering, this follows an optical path, specular path. And the HV component in this case too is normally very low. And the HH and VV have opposed phases. Okay. And over volume scattering, all components are normally very high because this volume scattering are made of this volume media are made of randomly oriented anisotropic particles. And in this case, the difference with the preceding cases is that over such media, HV has you will measure strong values in the HV channel. Okay, So strong HV means volume. Okay. Large HH plus VV means surface. Okay. And small, large HH minus VV means double bounce. Okay. Of course, these are interpretations. Okay. You will get this exactly if you go into an anechoic chamber, you measure metallic media with specific conditions. Okay. So don't, we must be careful not to overinterpret or very often we see, especially young scientists, they say, okay, I'm just separating single bars from double bars. No, you're not separating. You are providing an interpretation for what you are looking at. It's something we need to be careful with this kind of interpretation. But it is gives you a good idea and of what's going on the scene. So here you see HH plus VV compared to the others, okay, it's much larger than HV and HH minus VV over the sea surface. So it's a good indicator of a sea surface scattering, okay. Compared to the other images, HH minus VV is very strong over built-up environment. In this case, the plane was, for this image, the plane was measuring from this position, okay. So what you see, the very bright line you see here, okay, they correspond to double band scattering on the street and the walls of the building. And HV, okay, is homogeneous a bit everywhere over the city. But if you make the comparison between HV and the other channels, here for once it had the same or maybe slightly larger than HH plus VV and HH minus VV. So this is the biggest difference. And when you color code these three channels, you will get this nice image. Okay. For your information, there are many ways of classifying polarimetric data, but there is one I found very efficient, developed by Definiens. I don't know if you know this. It's a German company who was doing remote sensing. And they, at that time we were using complex statistical distribution, and they just took the color-coded image, okay, and they applied some simple classifier for each channel, and they got very good results at the end. So sometimes a simple approach is better. So from this image, if you know how to deal a classification, a color-coded classification, you can really separate most of the media you are looking at, you have in this scene. Okay, so if you remember well, we define a way to transform one scattering matrix from one basis to the other. Of course, I will not go into the detail. There is exactly the equivalent for the T matrices, for the coherency matrices. Okay, exactly the same transformations. The thing is that you don't operate it the same way. For scattering matrix, you have this kind of transformation. T means transpose. Here you need to use the inverse of a transformation. Okay, you can do exactly the same with the covariance matrix. As we said before, dealing with HH, HV, or HH plus VV, HH minus VV, and HV is exactly the same. They are related by a linear transformation. So you don't lose or you don't create information. So now what we saw today are, today we saw different ways of representing the same information. Okay, which starts from the description of the polarization ellipse. We said now when we do two acquisitions, when we meet a horizontal or vertical wave, we require different Jones vectors. If we put them together, we have a matrix which contains all the information that can be measured from the polarimetric point of view. And we define some vectors derived from this matrix representation. And from these vectors, we could define some covariance matrices. Okay. These are not, if you talk to people doing signal processing, this is not a covariance matrix. It's just a rank one covariance, because we take only one vector and we build this matrix from a single vector. And covariance matrices is meant to be an expectation. We are far from doing an expectation. But, okay, I will go over this. We know that all these representations here are defined. The Sinclair matrix is made of three complex coefficients, okay, makes 6 degrees of freedom, remove one, which is the absolute phase, and then we get 5 parameters to describe 3 amplitudes and 2 phases, okay. And when we transform this Sinclair matrix to C or T, we don't create any information. So we know that all these representations here are related by this number of degrees of freedom, which is equal to 5. So what does it mean? We start from the Sinclair matrix. We have three amplitudes, 3 moduli, 3 phase differences, 5 degrees of freedom. When we start from S, when we create the Keno matrix or the currency matrix, we have 9 real parameters. Why 9? Okay, because this matrix here is here. This matrix is 3 by 3. We know that by construction, it is Hermitian. So it means that these coefficients here are complex conjugate of this one. So we have 1, 2, 3 real parameters, and these 3 here are complex. So we have 3 complex, means 6 parameters, 6 real parameters per 3 means 9 coefficients. So it's like multiplying. We are creating information without information, so this cannot be from this physical point of view. So it means that these 9 real Heinen parameters, in fact, they are not independent, and they are related by the so-called target equations. Because at the end, when you compute these parameters and you relate them to the ones of the Sinclair matrix, you see that they are, in fact, related by 4 target equations. To this, 2A0, B0 plus B is equal, in fact, to this by construction. So we preserve the number of degrees of freedom. Okay, when we want to apply this to remote sensing, and I am now just preparing the speech of Carlos, we want to analyze real SAR images, and you saw yesterday that the first thing to do when you analyze a SAR image is to look at it, of course, and if you want to analyze it in deep way, you just need to apply a spherical filter to understand what you're looking at. And okay, now you know what the spherical filter is. It is the spherical is a coherent effect, and it comes from the combination of several contributions from different scatterers into a single resolution cell. And the difference, as I said yesterday, the difference between this pixel and this very dark one close to it, it's just that we had a different realization of these contributions. Okay, you have a, and it gives you a granular aspect, and it's very annoying when you want to analyze SAR images. Okay, so the objective of spherical filtering is to sample several realizations in a spatial neighborhood of each pixel and to average them in order to reduce the variance of the estimate. Okay. Yongsen Lee was very famous for deriving the famous Lee filter, and he, in fact, proposed to export directly the spherical filter from scalar images to the polarimetric domain by simply averaging covariance matrices. Okay, the same way we average intensities in monovariate images. So you start from a noisy image, okay, covariance image, and then you average several of these matrices taken sample into a neighborhood of the pixel you are considering. And what is the influence of this on the polarimetric information? It is enormous, and this is why people have been working on polarization analysis for many years. Okay, because when if you remember when we were measuring Sinclair matrices, 5 degrees of freedom, we make our transformation. We know that we keep the 5 degrees of freedom, but suddenly, when you average these parameters, these equations here are not verified anymore. You break this relationship, and then you end up with something you don't know how to analyze this from the polarimetric point of view, and this can be imaged this way. You have a for each sample you are taking in the neighborhood, you have a singular matrix, you transform it to an incoherent representation, okay? After you average all these incoherent representation and you have a kind of blurred view of what you're looking at from the polarimetry point of view, you don't really know what you want how to characterize this average representation. And the link to a better interpretation is to take this average representation and try to analyze it using a decomposition theorem, decomposition technique. The objective of this decomposition technique is to start from this average representation and extract a representation which can be assimilated back to a scattering matrix, something we know very well. Okay. Something we can analyze the orientation of, we can have an interpretation. And this is done by applying so-called decomposition theorems. Here I represent some old ones today. I would need several slides to put all the names of the decomposition techniques. Okay, now many ones. Carlos will show you some of them, and this morning, and during his presentation this afternoon. So this is the end of my presentation. So today, if I want to summarize what we saw, we just started from the description of the propagation of a very simple field corresponding to a plane wave. We showed that the polarization information of this wave could be described by a polarization ellipse characterized by 4, and you should take the sign of tau, which means 5 parameters. Okay, 4 parameters. Sorry, and so it was our way to understand what's polarization, what was in fact the polarization of a wave. We saw that when you do a fully polarimetric acquisition, you emit one polarization and you receive into polarization basis, and you need to make 2 acquisitions in order to build a 2x2 singular matrix, which is symmetric. And we ended with the incoherent representations that are needed to apply speckle filter. The good thing when you apply a speckle filter is that you reduce the variance of your estimate, perfect. But from the polarimetric point of view, you destroy what you took a long time to understand before. And this is why people need finally to apply these decomposition techniques to go back to something they can understand and analyze. Of course, this, as you can see here, decompositions can be performed from a mathematical point of view, from a phenomenological point of view, from some of them are really application specific, and there's a wide variety of possibilities. So, Carlos, if you want to, you can take the floor. So this afternoon you will. You will be able to apply decomposition techniques onto polarimetric images, and you will work on the famous San Francisco image.
Oui, c'est ici. Je peux voir, je vais vous montrer une chose tout d'abord.
Vas-y.
Oui, c'est la 2. Vous pouvez me montrer les livres, je peux vous montrer les livres d'application.
Ah oui, c'est vrai.
C'est vrai, comme c'est cartonné. Vas-y, ça. Voilà. Je ne sais pas où on est. Okay. Okay, thank you, Laurent. For me, it's a pleasure to be here and to talk to you about polarimetry and what we have learned in polarimetry in the last 20 years, and we can apply in the new sensors. First of all, I would start from the end, and I would like to make you aware about one work we published, I mean, few years ago, that was funded by ESA. It was a project funded by ESA trying to collect all the work that was done on polarimetry until that 2020, I think, more or less. So here you have this book. You have the theory, but the most important thing is that the book is plenty of applications. So where you can see which are the advantages of polarimetric data. And the most important thing is that the book is for free. You can download all the chapters if you want from a Springer website. So you have there, you have the theory, you have the applications on different domains, on land, on ocean, on cryosphere, on urban, on forest. So you have all the applications that can be, or that exploit polarimetric data. Okay, I just remember that. And now, let's go to here. So Laurent already introduced you the main descriptors for polarimetric data, and one of the most important things is the interpretation of this data. And for the good or for the bad, you need to put statistics into it for the correct estimation, especially due to the difference between point and distributed target. And that's why we need to introduce this statistical information that will help to understand the data, and is highly coupled with the physical interpretation of the data. So here you have our contact information. So feel free to send an email in case you have questions or whatever. I mean, I'll be glad to answer your email. I mean, please allow us a couple of days as to answer the emails, because my relation with email is not very good at the moment. Okay. Okay. So let's go. The outline of the presentation is going to be like this. First of all, I need to introduce you the statistical principles of SAR data, because on that I will construct the polarimetric SAR data statistical description. And as already Laurent introduced, I will explain the need of the spectral noise filtering, of the estimation of information in the case of polarimetric data. So first of all, what is a speckle in a SAR image? So on top, you have an RGB image where all the channels. So basically, polarimetry brings color to our lives. So you have gray pictures, but polarimetry is nice because it brings color. Here's in Oberpfaffenhofen in Germany at DLR. On the bottom, you have the optical image. But what is a speckle? If we increase the resolution, basically, a speckle is this salt and pepper aspects of the SAR images. Okay, in here we are plotting just the amplitude of the BB channel, and you see that the image is completely covered on this salt and pepper aspect. So this salt and pepper thing is a speckle, which prevents the extraction of geophysical information. So in this lecture, what I'm going to show is how do we interpret this, how we remove it, just to improve the images or the data. Okay, so which is the origin of speckle noise? So basically, as Laurent already introduced you, when we use SAR data, what we make is a convolution between the real SAR image, which is given here by you, and H, which is the impulse response of the SAR system. So what we have is the value of a given pixel is the coherent combination of all the individual scatters within the impulse response of the SAR system. And why this? Because we have, or we see targets, we see scatters at the resolution of the wavelength. So if we have a resolution of 10 by 10 meters, like in the case of Sentinel-1, our wavelength is lower than that. at C1 is about 30 centimeters. So we see targets at that resolution. So that's why we see many of targets inside. So what we have is the coherent combination of L, a given number of scatters. So depending on the number of L, we can have different models. If we have L equal to 1, we have only one target, we have a point target, and we don't have a speckle. We don't have noise. We don't have statistics at the end. If L is really large, to the infinite, what we have is a fully developed speckle. It's what we have seen before. And that's why we need to introduce statistics. And in the middle, when L is large, but not large enough, is the most difficult problem. Because in that case, we cannot use statistics, but also it's very difficult to have a numerical solution. So that's the worst case. L can be also itself a random variable. In that case, our model gives rise to the texture. We won't analyze that. We will focus only on the fully developed speckle. So in order to understand which is the physics behind the speckle. Okay, so basically what we have is this. We have a coherent addition, the random walk. Okay, we are adding vectors because the most important thing about SAR is that SAR images are complex. So every pixel has an amplitude and a phase. So when we combine things, the system is coherent like lasers. Lasers are coherent systems. So the response is just a coherent addition. Okay, so basically, if L is large enough, we end up with this expression in here. So as it is complex, we can work in the polar coordinate system or in the circular coordinate system. Okay, so we can work with real and imaginary part or amplitude and phase. And they, as you know, they are both related. So which is the particular case about a speckle? If you have this expression in here, so if all these arrows, if all those vectors add coherently, we have a very large amplitude. If they construct in a destructive way, okay, the amplitude of the total vector is very small. So this is what creates a speckle. A speckle is nothing more than these coherence patterns, this interference pattern. So in that image, so the bright points corresponds to points where all these vectors add coherently. And dark points are all those pixels where the interference is destructive. So that's why we see bright and we see dark points, because at the end, a speckle is nothing more than an interference, like in the case of lasers or in the optical sense. Okay, that's when we have enough targets in the resolution cell. But what happens when in the resolution cell we have only one strong target, like the corner reflectors? So in this case, what you have is this detailing here. It's a corner reflector. So in this case, the response is totally determined by the response of the single target. So in that particular case, the pixel, the value is totally deterministic. So if you take the radar cross-section, you could determine the size of the corner reflector. But in the case of the fully developed speckle, due to this complexity, which we have seen here, we are not able to predict the response. So therefore, we take a speckle as a statistical variable. But it's not a statistical variable, it's a pure deterministic. But the complexity of this process is so strong that the only ways to analyze them is to take this process as a statistic. But remember, a speckle, proper definition of a speckle is that it's not a noise. It's just a coherent addition. The complexity is so large that we cannot afford an explanation for every pixel, because for every pixel, we would need the complex characterization at microscopic level. So this is not affordable. Okay, that's why we need to talk about statistics. Okay, so let's going to construct this physical interpretation. So what we have under the hypothesis of completely developed speckle, okay, so we have large number of targets within resolution cell and none of them is dominant. Okay, taking of this hypothesis, that the amplitude and the phase of each individual scatter are not related, okay, are not related among them, and the phases of the individual targets are distributed between minus pi and pi, we can consider that, or we can characterize the SAR image as a complex distribution, complex for the real part, complex for the imaginary part. The mean of the real and imaginary parts are 0, okay? The standard deviation that characterize these Gaussian processes are the same, and the most important thing is that the real and imaginary parts are equal to 0. Basically, what we are taking here is the central limit theorem. So all of you have known perfectly this theorem. We apply that for the real, for the imaginary parts, and we then construct the statistical model for a single SAR image. That's why, okay, a SAR image for the amplitude has a Rayleigh distribution. So we combine the Gaussian for the real and for the imaginary part. We make the change of variable, and we transform these uncorrelated Gaussians for the real and the imaginary part for a Rayleigh distribution for the amplitude. For the intensity is an exponential, okay? And for the phase is uniform. So that means that in the case of SAR images for distributed targets, phase information bears no information about the target because all the values of the phase have the same probability. In the case of point targets, that's different because the phase has information about the target. But for distributed target, for a single SAR image, the phase has no information about the target. And the amplitude and the phase are uncorrelated. That comes from the fact that the real and the imaginary part are also uncorrelated. So these are how this distribution look like for different values of sigma, the standard deviation. Top left, you have the amplitude, the Rayleigh. On the right, you have the intensity. And on the bottom, you have the uniform distribution for the phase. Okay? Just if you have any question, don't bother to interrupt me. Just raise your hand and I can clarify your doubts, if any. Okay? So that's how we characterize SAR images. Okay? So where is the information in this case? Where is the information in the speckle? Okay? So basically, if we take the intensity, because as I said before, the phase bears or has no information about the target, so we look only at the amplitude or the intensity. So let's look at the intensity. So if we look at the exponential, we see, as you know, a statistical variable can characterize in many different ways. The first way is to have his probability density function. The second way is to have its statistical moment. So in the case of the Gaussian, or everything derived through the Gaussian, the statistical or the relevant statistical moment are the first and the second order moments, means and variance. So if we look at the mean and the variance of the exponential, we see that both of them have the same value, 2 sigma square. Okay, so basically, okay, the information, okay, is contained into the mean value, not the variance, because the variance is the variance around this main value. The particularity in this case, which will determine the nature of the speckle noise, is that the variance equals to the means. Okay, so if we are interested into the mean value, which brings the information about the radar cross-section, everything which is not mean value for us is noise. So the variance around this mean value for us is noise. So that's why we need to assume a speckle as a noise. Okay, so which is the model we are going to use? Basically, how do we relate this noise with this useful information? So if we take a look to the distribution of the SAR image intensity, as I said before, it corresponds to an exponential, so no problem. Mean value equal to the variance. So let's going to remove this variance, 2 sigma square, from the noise. So therefore, we can write the intensity as given in here. intensity is 2 times sigma square n, where n is our noise, and 2 sigma square is our mean value. So making this change of variable, we can derive the probability density function of n, which is our noise, which is an exponential. And in this particular case, the expectation is equal to 1 and the variance is equal to 1. So as you can see, the mean value modulates both the expectation, the mean value, and the areas. So therefore, a speckle, if we try to describe the speckle in a noise model, the relation between the useful information, the mean value, which corresponds to the radius cross-section, and the noise is multiplicative. Okay, it's not the very well-known additive noise models we all know, which appears in all engineering. In this particular case, the model is multiplicative. Okay, but I want to recall you, or to try to bring the point that, again, a speckle is not a noise. It's a pure electromagnetic measurement. The problem is that the complexity is so large that the only way to tackle this complexity is to assume that this is a noise. That's why we end up with this multiplicative noise model. Okay, so for instance, if you take one SAR image of the one area and the area doesn't change anything, even the position of the satellite doesn't change, you will obtain the same image. So this is against the definition of a noise because it does not change. Okay, the problem is that the complexity is so large that, as again, the only way to tackle this complexity is to assume that it is a noise model. Okay, and the problem is that the noise does not follow the easy to handle additive noise. Multiplicative noise is very complex to handle. Why? Because we cannot use useful usual techniques. I mean, one of the most usual techniques to tackle the presence of white noise is basically you increase the power of your signal. Okay, you increase the signal to noise ratio. In multiplicative noise, this doesn't work because if you increase the power, you increase the variance. So the signal to noise ratio is constant with the power. So this is one test of this physical behavior of the speckle noise. So here I have one image here. So I took this red square where I calculate through patches the mean and the standard deviation of the HH and the BB channel. Okay, and as you can see, the mean is equal to the standard deviation. So everything is close to the slope 1 line. Okay, so it means that in order to handle a speckle, we cannot increase the power of our SAR system because this doesn't work. Okay, so we have to tackle a speckle noise, or we have to remove a speckle in different ways. Okay, so we have created the statistics, the physical explanation of a speckle for a single SAR image. What happens with polarimetry? As Laurent explained you before, in the case of polarimetry, our system doesn't take one image, but takes a collection of SAR images, playing with the polarization at transmission or reception. Basically, you measure the scattering matrix. You can vectorize the scattering matrix in the vector case. So here you have a HH, HB, BB. Okay, so which are the properties of this target vector? So in case we are in point targets or deterministic targets, each of these SAR images is deterministic. So the vector is completely deterministic. Okay, no problem. Okay, so we can work with that. But what happens when the vector refers to a distributed target? So in that case, the 3 images present a speckle. Okay, so our measurement is no longer a single SAR image, but a vector. In the case of a SAR image, we characterize our measurement, our SAR image, through the mean and the standard deviation. In this case, we have a multidimensional signal. So how do we characterize the statistics of a multidimensional signal? First of all, the first order moment is the mean of the vector. But now it comes to analyze the variance of a vector. And the variance of a vector is what makes polarimetric data so rich, as Laurent presented before. Okay, same. We take our starting point is the complex Gaussian distribution for a single SAR image. Okay, so remember, we have this for each one of the SAR images. So the first option to extend this idea to a vector would be to consider the images independent. So in the case of independent, the probability of the vector or the scattering matrix, if you want, would be the product of the three SAR images, or the product of the three exponential distributions, okay, or the or complex SAR images. Okay, no problem. We can do that extension. If we go to the first order moment, this model would predict that the mean of the vector is equal to 0, which is okay. But the problem is that when we want to characterize the second order moment of a vector, and the second order moment of a vector is a covariance matrix, the only possible matrix that we can use or that we can impose onto the data is the diagonal matrix. This is the only model. So as Laurent presented before, he introduced the covariance matrix. So in that case, the only possible covariance matrix we can have is the diagonal matrix. So no polarimetric information at all. So this model is not valid. Why? Because SAR images are correlated. Okay, this previous model, the idea behind is that SAR images are not correlated. As we said, we impose independence between SAR images, but we cannot impose independence. Okay, so if we extend, okay, as I said before, how we can characterize a random variables by the PDF, okay, by the moment generating function, or by the statistical moments. In the case of the Gaussian, it's so easy to handle it that we only need to use the first and the second order moments. Okay, so if we consider a K vector of correlated SAR images, the PDF is the one shown here, which is the multidimensional Gaussian complex Gaussian distribution. And the most important parameters of this probability distribution is the C matrix, which characterizes completely the matrix. The distribution. As we said before, for SAR images, the statistics are fully characterized by the variance, because the mean is equal to 0, in the case of complex, okay? In the case of multidimensional data, the most important parameter is the covariance matrix, which, if you remember, Laurent presented before, which is the matrix that contains the polarimetric information. So as you see, there is a connection between the statistics and the polarimetry. So therefore, there is a connection between the statistics and the physics. Okay? The problem is that this C matrix is defined through the expectation operator. It's a statistical measurement, but it is a good starting point. So this is the basics for the statistical descriptions of polarimetric SAR data for distributed targets. Okay? The idea is that in the case of the Gaussian, as I said before, the Gaussian has the magic property that to characterize the statistics, higher order moments depend only on the first and the second order moments. The first order moment is equal to 0. The second order moment is the covariance matrix. So we only need the covariance matrix to characterize the data. So therefore, the covariance matrix fully characterizes the data. So that's the only parameter we need to measure, need to estimate, to characterize completely the data. It's okay? Who? A break? Okay, so let's make a break. No problem. Okay. Okay. So I have understood that you have already a copy of the slides of this session. So they sent an email. So you have them. You should have 2 PDFs. Okay. Section 1, section 2. Also, during the session, you should receive the notebooks for this afternoon, or you will have them afterwards, okay? So for the session, I will go into the details later, but you will have 2 notebooks. So you have to code, okay? But you will also receive the solutions. For the second notebook, you will have 2 solutions. One of the solutions is where you have all the functions explicitly programmed within the notebook. And the other solution is using internal functions of NumPy. So it's a different way. So you have in total 5 files, okay? But we will go into that later. Okay, so let's continue where we left it before. And remember that we were characterizing the statistics of the PolSAR data, and basically the statistics, okay, are characterized by the covariance matrix. That turns to be the main polarimetric observable for distributed scatters. So you can come to the covariance matrix from the polarimetry itself and from the statistics. So both are related. So the idea behind this is that for distributed scatters, polarimetry must be understood statistically. So this is why somehow polarimetry is a bit complex to understand. I mean, it's not like understanding optical images, where you have the radiometry of the images and it's super easy to understand. Even my nephew, which is 5 years old, is able to understand because are big classical pictures. In this case, in the case of SAR, there are 2 layers of complexity. The layer of that we are dealing with microwaves, so we are not used to understand microwave. And the second is that we need to understand the information from a statistical point of view. Okay, for distributed targets. For point targets, this is not the case. For point targets, you just interpret deterministically the point. Okay, so remember, we have the covariance matrix, and the bad point of this guy here is that to interpret the covariance matrix, we need to estimate the expectation operator. Okay, everything is defined in terms of the expectation operator. Okay, so let's go later on. I will show you how to understand this information. Okay, so this is our distribution of the multidimensional SAR data. Just for you to know, in this case, we are considering 3 SAR images. Okay, HHSB, but this is exactly the same for interferometry. You have 2 images, S1, S2, and you calculate the correlation. It would be the same for multitemporal. You have 125 images, so you will have a 125 times 125 covariance matrix. Okay, the model is exactly the same for any multidimensional SAR data. The difference will come from the physical interpretation. So in the case of interferometry, the correlation, maybe one of you have already worked on interferometry, so the interpretation is in terms of topography or subsidence. If you work with differential interferometry, for polarimetry is the geometry of the target, for multitemporal is changes, for multi-frequencies is characterization. But this model in here extends to any kind of multidimensional SAR images. The only difference is the number of images. So of course, the larger the number of images, the worse to work with these guys, okay? Because they become large, okay? They become, and you enter in the, for instance, you go into the big data thing, I don't know. For instance, we had a project on ESA, and we were working with a temporal series of 1 year of sentinel images, and we were having covariance matrices of 1000 times 1000 for each pixel. So, I mean, you can simplify them. But what I want you to know is that this model is valid for any type of multidimensional SAR data. If you are interested in multitemporal, which is the golden application for Sentinel-1, for instance, you can use this model too, no problem. Okay, so let's go back to reality. Let's go back to polarimetry. So this is how do we characterize the data. So the first order moment is 0. So first order moment has no information. All the information is contained on the covariance matrix. So if you go to the PDF, you see that the only parameter this PDF has is the covariance matrix. So all the information is in this guy here. Okay? So how do we interpret the information of this matrix? So this information, I will go later on, but basically on the diagonal, okay, you have the power information. You have the power of transmitting H, receiving H, and all the possible combinations. The off-diagonal elements refer to the correlation, the statistical correlation between the images, how correlated they are, okay? So we can interpret this correlation information in absolute terms, as I gave here, the expectation SK-SL complex emission conjugate, okay, and we get this information. I mean, the correlation is essentially how similar statistically are both images. The advantage of correlation is that we can use correlation in a normalized wave, as given in here. And again, if some one of you have already worked on interferometry, you will identify this as the interferometric correlation. In this case, it's the polarimetric correlation. So the interpretation is different. In the case of interferometry, the phase contains the topography. In the case of the radar of polarimetry, this phase will contain information about the geometry of the target and the water content of the target. That's the two main sensitivities of these guys here. So basically the correlation, the amplitude goes between 0 and 1. 0 means that the images are totally decorrelated, so they are not similar. Correlation to 1 means that they are the same image. And the phase, of course, the phase, okay? In this particular case, the phase of polarimetry for the three terms, HP, HBBB, and BB, all the combinations, will contain information about the geometry, okay? This complex correlation information represents the most important radar observable for polarimetry, in the same way as in the interferometry. Okay, in interferometry, it brings information about topography. In the case of polarimetry, brings information about target geometry. So we can classify the targets. Okay, so let's go to overview all what we have on the case of multidimensional SAR data descriptors. Okay, so remember, we are under the Gaussian assumption, first order moment, second order moment. In the case of polarimetric SAR data, the first order moment is the scattering matrix, the SAR images. Okay, so we can have this information in a matrix or in a kind of target vector, as Laurent said before. How do we describe the scattering matrix? We can use the covariance matrix. In here, I also wanted to generalize this idea. So I consider M images. In the case of polarimetry, in the monostatic case is 3 images, in bistatic case is 4 images, and so on, okay? So for point targets, for deterministic targets, these guys here contain all the necessary information to characterize the target. So when there is no speckle, we can extract information from a single pixel. Where do we have this type of targets? In the case of corner reflectors, in the case of urban areas where you have strong canonical scattering mechanisms. What happens if there is a speckle? The first order moment, the mean value equals to 0. So it means that there is no information on the mean value. All the information is contained on the covariance matrix that, as you can see, characterize completely the distribution of the data. So when we go to distributed targets, for natural targets at the end, okay, forests, crop fields, agricultural areas, and deserts, and so on, we need to stick to this. In the case of urban areas, you can have a combination of both descriptions. But whenever you want to analyze SAR images, you have always to struggle between the differentiation between point targets and distributed targets, because the tools, the descriptors you use to work on one type of target and on the other type of target is in here, okay? They cannot consider in the same way, okay? So this is, again, our important estimator, important parameter, the covariance matrix. So we need to estimate it. So we need to estimate the expectation operator. It's a statistical operator, and we need to estimate the statistical operator. So as Laurent presented before, we have to struggle, or we have to tackle with the heterogeneity of SAR images, because the SAR images reflect reality. And in reality, what do you have? You have homogeneous area, distributed targets, like the grass area that I indicated in red, okay? You have point targets like the plane, which is circled in green, or you have super heterogeneous areas like the one circled in with the yellow square, where you have a combination of grass, buildings, so it's super complex. So we have to tackle with that. So how do we do with that? In the case of homogeneous areas, okay, our objective is to maintain the radiometric resolution, is to estimate the mean value. In the case of point targets, as all the information is contained in the pixel, what we want to maintain is the resolution of the pixel. We don't want the resolution. We don't want to lose that resolution. But in reality, we have a mixture of both things. So all the super fancy speckle noise filters you might find in the literature, basically, all of them define different ways to tackle this heterogeneity, trying to adapt to the local morphology of the data. Okay? You have super old filters like the one we defined 20 years ago, or you may have all the fancy speckle filterings based on artificial intelligence. But the basic of all of them is to differentiate between these two in a more or less complex way. Okay? Which is the most straightforward operator to estimate the expectation operator? The maximum likelihood estimator of this expectation operator is what we call the sample covariance matrix, which corresponds to the multi-look. So basically, what we make is to estimate the expectation as the mean value of a given number of pixels in a region. So first of all, if we want to estimate the covariance matrix, all the elements must be estimated in the same way. You cannot apply different filters to each element, because otherwise you will break the polarimetric relations. Okay, let's say I cannot filter the first image with 1 pixel, the second element with 10, the third with 25. No, all of them have to use the same number or the same way, have to be applied in the same way. Okay, so therefore we make an estimation of the covariance matrix, which is set n. The advantage is that we can use any type of shape to estimate this multi-look. Normally, the most useful way to estimate is to use a square boxcar, 3 by 3, 7 by 7, 11 by 11, always an even number, because if you put an odd number, you move the images by half a pixel. So it's 3, 5, 7, 11, or you can use rectangular, or you can use adapted, okay? And this is where all these new fancy filters go. They go into the direction to adapt the spatial filtering, okay? So if we stick to the maximum likelihood, which corresponds to the boxcar, okay, we don't pay attention to the morphology. So we obtain capability to estimate the data at the expense of losing a spatial resolution. Okay, and this is one of the worst things you can do with SAR, because you cannot expend millions of euros trying to get a super powerful machine to obtain super high resolution, and you lose the resolution with a simple filter. So it's a worth of money. Okay, so that's why you need to go for advanced filtering. That's to keep this capability. So therefore, we don't estimate the C matrix. We make an estimation of the C matrix, is what we call the sample covariance matrix, which at the same time is a multidimensional random variable. Okay, it's an estimation of the C matrix. Okay, for all of those of you who are interested in the statistics, okay, the PDF of Zn is what we call the Wishart distribution, the complex Wishart distribution, which has this very complex shape. Okay, but the most important thing is that it only depends again on C, on the covariance. There is no other parameter. Okay, the Wishart is somehow difficult to handle, but still you can go with it. Okay, one of the main advantages of the Gaussian model is that maybe it's not the most accurate, perfect model, but nowadays it's the only model we can handle analytically. I invite all of you to look for new models and to work on them analytically. It's super heavy, okay? If not impossible. Okay, together with Laurent, we were analyzing the Wishart distribution 20 years ago, and it was super heavy at that time. So the Gaussian maybe is not the best model, but at least is the model that works everywhere and that model that you can handle analytically. Okay, and there are many tools in the literature to work with complex. You can draw insights from economics, from biomedicine, from engineering. So there is a lot of work done on the Gaussian. Okay, so whenever we want to estimate the covariance matrix, one of the main problems using this model is that in order to estimate correctly the covariance matrix, you need a minimum number of samples, and this minimum number of samples corresponds to the dimension of the data. Okay, so if we are dealing with polarimetry, the dimension is 3, so the minimum number of samples we need to estimate correctly the covariance matrix is 3. Now, if I go to multitemporal and I have 1,000 images, the problem is that the minimum number of samples to correctly estimate that matrix is 1,000. And sometimes you cannot afford for that number, so you run into problems. Okay, it's just one of the limitations, which in the case of polarimetry is not really a limitation. Okay, so this is again a map of the distribution of the data. So we start with single SAR images, the complex Gaussian distribution, we transform into multidimensional, we go to the Gaussian, we estimate the sample covariance matrix, and we end up with the complex Wishart distribution. So everywhere is the covariance matrix that describes the statistics of the data. Okay, so let's go with some examples. On the left, you have the original data, which is L1 PolSAR data over Pfaffenhofen in Germany, near the city of Munich. So you can see the speckle, okay, you can see the forest in green, you can see the crop areas in red, some urban areas in the middle. On the left, you see the speckle. On the right, you see 7x7 multi-look image. So of course you don't see a speckle, but if we go to the details, you see the problem of the multi-look. In the middle, you have this line of corner reflectors. Okay. On the left, you have these details. So as you can see, of course, I remove a speckle, but at the expense of losing the spatial resolution. So what you see here, these squares are the impulse response of the filter, because the corner reflectors and the point targets are behaving as delta functions. So basically, if you convolve the image with the filter, what you see is the impulse response of the system. That's why you obtain the squares, the 7x7. So we need new ways, we need improved ways to estimate the correct information in the case of distributed targets, but while keeping the spatial resolution. Okay. One of the old filters that we use is the Lie filter, which basically is the minimum mean square error. So basically, the idea of the filter, if you put all the equations, is that the filter analyzes the variance of the data. So the essence beyond the equations is that if I'm able to explain the variance of the data with the Gaussian model, it means that we are in the case of a distributed scatter. So in that case, the best estimator is the expectation. If we have a variance that is much larger than the Gaussian model, therefore the Gaussian model is not able to explain the variance into the data, it means that we are in a point target. So in that case, we don't need to filter. So the final idea is that, as given in this blue explain the variance, you can see that the estimated intensity is the original. So we have a balance between the mean and the original value. Okay, so this is the result. Okay, so as you can see, this is for a single SAR image. As you see in the point targets, the filter is able to identify that we are under a point target, so we don't filter. And in the homogeneous areas, okay, we try to estimate the expected value, the mean value. So we range between both of them. Okay, the extension to the polarimetric case, and this is super important, we have to deal all the elements of the covariant matrix in the same way. So basically, the idea is that we calculate this B parameter on the span, which corresponds to the total power. We calculate B, and we extend this B parameter to all the elements of the covariance matrix. So as you can see, our estimated matrix C corresponds to a balance between the expected value, the mean value, and the original value. Okay, you can do it with in a refined way, doing more or using more adapted windows, which is not really important. And this is the case we obtain here. Okay, so what happens if we go on the left, you have the original, on the middle, you have the one obtained with the Lie filter, on the right, you obtain the multilog. Okay, on the large scale, you don't see difference, but if you pay attention to the details, you see the differences in terms of the spatial resolution. Okay, and the most important thing, and this is super important, you see that the filter doesn't change colors. And in here, color is very nice. Color brings joy to our life, but color means also polarimetric information. So if you define a filter and you obtain a rainbow images, is that you are destroying the polarimetric information. Okay, so as you see, the original, the multilog, and the refined Lie filter, all of them keep the colors, keep the polarimetric information. If you go into the point targets, the corner reflectors, okay, which are scattering matrix is diagonal, 1, 0, 0, 1, all of them obtain red. So they keep the polarimetric information. And this is super important. And this is assured by the fact that you process all the elements of the covariant matrix in the same way. So you have to think that you are estimating a matrix, so all the elements need to be estimated in the same way. If you start to process the elements differently, you will start to introduce biases in the polarimetric information. So if you make an RGB composition, you will obtain a different color, which is wrong, okay? It may look nicer, but it's wrong. And something is super important, and this is something I have seen during many years. People try to identify red with double bounds, blue with surface, green with volume, okay? I can change the color map and the information is maintained, okay? This is the standard application, but you can do whatever you want. Always you have to be consistent, okay? Try to identify double bounds with red, green with volume, and blue with surface. I mean, it's the way we do it, but you don't need to understand the images in the terms of colors. You need always to give, together with the image, the color code you have given to the polarimetric images, okay? Questions? No? Okay, so let's go to the second part of this lecture. Okay. Where do we are? Laurent presented this morning polarimetric information, okay? And we end up, remember, we end up with the covariance matrix, okay, which contains the physical information. In the lecture before, I went to the statistics, and I also end up with the covariance matrix. So as you can see, if we take the two lines of the two lectures, on the lecture in the morning, you arrive to the covariance matrix through a physical interpretation, okay? And in the second lecture, I have arrived to the covariance matrix through the statistical way. So that means that the physical information, if you combine the two of them, the physical information must be understood stochastically. That's the main, if you have to keep one lesson of this lecture today, is this: the physical information acquires only relevance in a statistics term. And this is why somehow polarimetry is a bit difficult to understand, because the information only comes from the statistical interpretation of the data, okay? Which is totally different to optical. It's not better, it's not worse, it's different, it's complementary to optical images because they see different things, okay? And this is, I hope that you got this message, because this is the message we wanted to give with Laurent: physics and statistics, okay? So now it comes, how the hell I extract physical information from this, okay? So here you have the contact information. So how many of you know about the Fourier transform? Okay, so for all of you who know the Fourier transform, target decomposition theorems are nothing more than the Fourier transform. And I will show later on why, conceptually, okay? And for the rest, I will try to give you the main idea behind target decomposition theorems, okay? The idea of Fourier transform is that you can decompose any signal in a given number of complex exponential functions, or the DCT, the discrete cosine transform, into different cosine function. So the idea of target decomposition theorems is precisely that. Try to decompose the covariance matrix into some basic building blocks. Okay, it's a decomposition technique. So I'm going to present the main ideas behind target decomposition theorems. I will differentiate between coherent and incoherent decompositions, and I will, if we have time, I will end up with some examples. Any question? Again, if you have any question, don't hesitate to raise your hand and you can interrupt me, okay? I prefer to spend half an hour in one slide to be clear than to go. The goal is not to arrive to the end. The goal is that what you got, you understood, okay? Okay, so What do we mean by target decomposition theorems? Remember that to describe our polarimetric data, we have two descriptors. A scattering matrix, which is useful, not filtered, if I can use this word, and that we use for point targets. Covariance matrix for distributed targets. So the basic idea of the target decompositions theorem is what I show in the simple equations, okay? In the case of coherent decompositions, our goal is to decompose the scattering matrix into a sum, into the addition of a given number of much simpler scattering matrices. And therefore, we hope that these simpler scattering matrices have a very clear physical interpretation. So we can derive the physical interpretation of the complex scattering matrix from the combination of the simple or physical interpretation of these basic or canonical building blocks. In the case of incoherent decompositions, remember, where we need or we use the covariance or the coherence matrix, what we do is exactly the same. We decompose our coherence or our covariance matrix in a given number of much simpler matrices, okay, that we are, or for us is easier to understand physically. So as you see, it's the same idea as the Fourier transform. I decompose a very complex signal in a given number of frequencies. I understand very well which is a single frequency, low frequency, mid frequency, high frequency. So here the idea is the same. I mean, to try to decompose into basic building blocks on the hope that the physical interpretation of these basic building blocks help us to understand the complexity associated with reality. Okay? It is clear for all of you? Or do I need to go again through the explanation? Because I want this to be clear, and the rest is just a walk from here. Okay? Okay, let's go to different examples of these target decomposition theorems. Okay? First of all, I will focus on the coherent decomposition theorems. Those decompositions only apply to point targets. Okay, and this division is super important. And I remember 20 years ago, there were fights in the conferences for those for or against decompositions. Okay, now it's quite established that coherence decomposition I normally use to describe point targets, and incoherent decomposition are used to describe distributed targets. Okay, it took some years to arrive to this conclusion. So the most basic decomposition, the Pauli decomposition, okay, which is used in many domains. In physics, is very used. So in this case, on the Pauli decomposition, we decompose the scattering matrix in this collection of 4 scattering matrices. Okay, as we are in the case of monostatic data, transmitter and receiver are placed on the same position. The fourth component is 0. Okay, so the first is single bounce, okay, which corresponds, for instance, to bare surface. Okay, in that case, the scattering matrix corresponds to 1, 1 diagonal. Double bounce is 1 minus 1, because there is one of the 2 reflections that change the sign of the signal. So therefore, we have 1 minus 1. And then we have volume, which is 0, 1, 1, 0. So you can already identify that the volume goes into the HV component. So this is quite a standard thing. Volume means lot of complex interactions because it's multiple bounds. At the end, volume is multiple bounds. So therefore, when you have multiple bounds, you have changes of polarization from HV to BH. Okay, that's why volume appears in HV. So, as you can see, these very basic building blocks allow a very simple physical interpretation. So now, the idea is how we decompose a general scattering matrix into this composition. Okay, so in this case, it's super easy, and you can see that alpha, which corresponds to the power associated to the single volume, beta associated to the double bounds, and gamma associated to the volume are obtained in this way. So the way to obtain the coefficients is given by this expression here. And the most important thing is that in this case, we are using the complex images. They cannot be obtained from only intensity. Because here and here, the phase between the SAR images play a role. Okay? So here is one example. Again, the Oberpfaffenhofen test site near Munich. Okay, so alpha is single bounds, beta is double bounds, and gamma is volume. So if I go to the third, you see the forest on the top, you see that the most of the information comes from gamma, which corresponds to volume that occurs basically in forests and in urban areas. As you can see, okay, for bare surfaces in the middle of this runaway of the airport, okay, all the components come from the largest components comes from the alpha, which corresponds to the bare surface. So therefore, we have decomposed this image into this, and this. Remember, and also this is something very important, is that normally these RGB images do not contain all the polarimetric information. Okay, also only partial information. And the most important thing, look in here that the Pauli decomposition I make to create that image, okay, considers the amplitude of HH minus VB. It's not the amplitude of HH minus the amplitude of VB. Because if I do it only with the amplitude, I won't see it's not the definition of the double bounds or the single bounds, etc. Okay, and this is very important. As you can see, I can interpret the complexity of the image on the left with the simplicity on the images on the right. Someone of you could argue that I'm extending this description also to distributed targets. Okay, true, it's totally true. But in the case of the high quality images like this, because this is airborne data, we can use it. Okay. There is a second decomposition which goes basically in the same in the same direction, which is let me. I don't know. I don't know, but there is supposedly someone of you know how to remove the ribbon on the. ¿En dónde? ¿Vale? Más que ¿sabes? Gracias. I mean, in this time of pandemics, we are used to all this. I have gone through all the teleconference software and I don't know any one of them. Okay, Pauli decomposition, okay? So here you have the interpretation. So let's go with a different decomposition, which is what we call the Kroger decomposition, which is a Danish colleague from Denmark, and Kroger, we did a second decomposition, which has one particular advantage. In that case, what we make the composition, or we decompose the signal into three elements, which correspond to the sphere, D-plane, and helix. The helix is a bit weird to estimate, but I mean, it's a kind of helix. So in that case, the sphere is equivalent to single bounds. the D-plane, in that particular case, we can introduce a rotation. Okay, we can have a D-plane rotated. And the second one, the third one, sorry, is the helix, okay, which has this particular scattering matrix. The advantage of this decomposition in front of the Pauli decomposition is that it's role invariant. The elements are role invariant. So that means that if we have a rotation along the line of sight, the parameters are unchanged. And this is super important. In the case of Pauli decomposition, the polarization depends on the reference, okay? In the case of the role invariance, our parameters do not depend on the reference we are using, okay? You can go to the literature and you can find how these parameters are obtained. So here is the decomposition. As you can see, we decompose our original matrix into these three different components: a sphere, D-plane, helix, and then you have the different parameters of the decompositions. The parameters K refer to the power, to the strength of each component, and then you have some phases associated to them. Okay, because again, everything is coherent, is related, amplitude and phase. Here is how do we decompose the signal. It's a bit more complex than in the case of the Pauli. The Pauli was super easy, super simple. Okay, in this particular case, it's a bit more complex. And the most important thing is that most of these algorithms are based on some kind of hypothesis that sometimes are violated. Okay, so you have to be careful with that. So the sphere, the KS is estimated directly with SRL, which in this case is not the HB reference, so the right circular, left circular reference. Okay, so you transform the scattering matrix for the horizontal vertical reference to the right circular, left circular reference. Okay, in order to D-plane an helix, you have this option in here. So you can have an helix defined to the left or to the right. So you need to follow these equations to obtain the different parameters and the phases associated to them. So there is a proper algorithm to derive the K values and the phases associated to the decomposition. Here is what you have. Okay, it's a different one. Okay, complementary to the previous one. So therefore, we can interpret our image as a function of the sphere, the D-plane, and the helix. As I said before, the helix is a kind of weird behavior, okay? But basically, as you see, remember that the helix, if we go back to the original equations, the helix is on the off-diagonal elements, HB. So somehow, it may contain information about volume, okay? So as you can see, the helix has the strongest values on the forest because there is this depolarization effect, okay? Normally, when you analyze polarimetry on targets, you need to analyze the polarimetric information in terms of the bounces. Single bounce, double bounce, multiple bounce, okay? Volume is multiple bounce. So you enter with a given polarization linear into the volume, a forest can be the case. Then you start to bounce everywhere, here and there. You have 26 bounces, and then you get back. So basically, as you may imagine, all the bounces, what they make is to transfer power from one polarization to the other. Okay? And this is why we identify volume. Okay? And position, we made the RGB. We could make the RGB also with the powers associated to the Kroger decomposition. You obtain a different information. Of course, all of them are coherent. You should not explain different set of colors, okay? Because both explain the same reality in a different way, but both explain the same reality. Okay? As I said before, coherent decomposition are strictly only valid for point targets. Okay, so what happens if we go to distributed targets? So we go to a second family of target decomposition terms, which are called the incoherent decompositions. So in that case, we decompose the covariance and the coherency matrices, not the scattering matrix. Okay? So remember that in order to obtain the in coherence, we have the filter in the middle. We have to estimate the covariance matrix. So let's go into this example. So therefore, we have different samples of the forest. Okay, we have sample 1, sample 2, sample 3, sample 4, and okay, m samples of a forest. So in each particular case, we have one realization of the same forest. Okay, you can think the same trees spread in a different way. Okay, so for each case, we have the scattering matrix as the covariance matrix. Remember that in this case, the pixels are random. So therefore, the scattering matrix has no information. The C matrix has no information because the C matrix is derived directly from the S matrix in rank 1 matrices. What we try to analyze is the average target. We don't want to analyze a particular pixel of the forest. We want to analyze the forest as such. Therefore, we analyze the average. Remember, we analyze the covariance matrix describes the distribution. We do not describe each individual pixel because the probability of a single pixel is 0. We describe the distribution. We describe the mean value of everything. Okay, so in the case of the forest, we describe kind of average forest. Okay, so in the case of the target of the coherent incoherent decomposition, we have two families of decompositions: model-based and mathematical-based. Model-based are those decompositions imposing from the beginning physical behaviors. Okay, they mimic somehow the decomposition of the scattering matrix. We fix single bounds, double bounds, and volume. Okay, therefore, the physical interpretation is super easy because I fix from the beginning, which is the physics of the data. In the case of mathematical based, I use some tricky mathematical operations to make the decomposition. They are super easy to calculate. They are somehow complex to interpret physically because the physical interpretation is not embedded into this mathematical based decomposition. At the end, for all of you, for those of you who know, all of them are more or less based on the eigenvalue, eigenvector decomposition. So there is no physics embedded into that decomposition. It's super easy to calculate, super neat, super clear, but lacks from a clear physical interpretation. This is the advantage of the previous one. Okay. The use of the model-based decomposition is super nice, it's very well, but if you fix something, they will find something. That's a problem with this decomposition. If you somehow assume that your decomposition has volume, for sure the decomposition will try to find volume. But maybe the volume is not in person. It's because you fix in advance. Okay? So Laurent presented this slide before. You may think, oh, okay, all these decompositions are super old, are not fancy, are not based on artificial intelligence. That's true, but all the decompositions that we have nowadays are born from this. Okay, and all of them pursue the same interpretation. Okay, I won't go into the coherent decomposition. Okay, I won't go into the hidden decomposition. I will go on the big square. So therefore, you have the model-based decomposition. The first one was done by Anthony Freeman from GPL. And there is a sequel of tens of decompositions, which basically are born from there. It's okay, I will focus on that. And for all those of you who are interested, you have just to follow the sequel of the papers because the beginning is in there. You can start with 3 parameters decomposition, 4 parameters decomposition, 5, 6, 7. You have all the sequel, but the basics is in there. Maybe it is important to mention, I will mention the band-style decomposition, which introduced some important corrections on the Freeman decomposition. Okay? And the second is the cloud decomposition, which basically is on the eigenvectors based decomposition. Okay? And we will combine all of them. So normally when we are dealing with a coherency matrix, okay, sometimes these decompositions are based on some assumptions on the type of target. In the general case, we have the 3x3 parameters. In the case of reflection symmetry, which is the most standard one, we assume that some of the elements are 0. In the case of the rotation symmetry, all of them are 0. In the case of the azimuthal symmetry, have this type of matrix. In the covariance matrix, the interpretation is the same. So some type of decomposition put these assumptions. The most standard assumption, which is more or less fulfilled in the case of polarimetric data, is the reflection symmetry, which assumes that the correlation between HB and BB is 0. That's why Sentinel-1, the correlation between HB and BB on distributed target is always 0. It's useless because it's 0. It's different from 0 only on point targets. Okay? It would be nice if Sentinel-1 would have HH and BB, but technologically it's much more complex. It's very, from my engineering point of view, it's super easy to make HB, BB or HB, HH. To make HH, BB is super complex and imposes a lot of restrictions, okay? So let's go to the Freeman decomposition. So in the case of the Freeman decomposition, we decompose the covariance matrix or the coherency matrix into 3 different scattering mechanisms: single bounce, double bounce, and volume scattering. So therefore, the goal is to find this decomposition coefficient. How do we obtain T as C as the addition of these simple scattering mechanisms? So the single bounce is single bounce. So the way to obtain the covariance matrix of the single bounce is this expression in here, CS. Okay, so you start from the scattering matrix, you rotate the matrix stochastically, and you arrive to this model for the scattering matrix for the paired surface in the case of the covariance matrix. In the case of the double bounce, you start from the scattering matrix. The important thing is that I can assume 2 different materials for the 2 surfaces. So some people has used that to identify the materials of buildings, for instance. Okay, you have this capability, and then you end up with this model for the C. Where do we have double bounce? Like given in this picture in here, on urban areas and on forests, if you have enough penetration, which more normally appears at L-band, P-band. Okay, it's very difficult to have that on case of C-band because you don't have penetration. And volume scattering, this is the idea. You have a kind of cloud of random needles. You make all the mathematics, all the magic of mathematics, and you end up with this model in here. Okay. Most of the target decomposition that derive from the Freeman decomposition try to derive more complex models for the volume, because at the end, the volume is the most difficult element to determine, because normally the weakness of the Freeman decomposition is that it overestimates the volume. So for all of you who have already worked on target decomposition theorems, for instance, the Banzai decomposition or the Sikulos Yamaguchi decompositions, all of them more or less try to improve the estimation of the volume component in many different ways, achieving, of course, better results. But as you can see, all of them start from this simple model. Okay, so here, this is how you decompose the covariance matrix. Of course, you assume reflection symmetry, which is the problem. You have 4 equations, 5 real coefficients. So it's an imposed problem. I need to impose some assumptions. I need to estimate something. So if the assumptions are violated, then your decomposition is wrong. If the assumptions are valid, the decomposition is okay. Okay, but despite all these limitations, the Freeman decomposition is super useful to classify or to interpret the data. Normally, this is the problem of the Freeman decomposition. As you will know, whenever we teach engineering 101, basically you can never have negative powers. Okay, you have only negative powers in the case of reactive loads on transmission lines. Okay, but this is not the case here. This is not physical, and this is one of the limitations of the Freeman decomposition. So basically, the Banzai decomposition and the Yamaguchi decomposition, after all, and the RE decomposition, which are colleagues, they try to overcome this problem, forcing that you never obtain negative values. This is the decomposition. Much better than in the case of the coherent decomposition. If you look to the forest, you see that all is concentrated on volume. So as you can see, for coherent, for distributed target, incoherent decompositions are super useful, because as you can see, there is a bit of surface, there is a bit of double bounds, because this is an L-band system, airborne, so you have some kind of penetration, so you have some information from the soils, some information for the trunks, for the double bounds. Okay, of course, you obtain double bounds a lot on the urban areas in the middle, where the DLR is, and also on the crops. If you see this squaring here, okay, this is corn, super regular plants, very well planned, so L1, so you have super double bounds there. Okay, and you have also volume on the urban areas. So this is a constant. You will see that it is a constant in polarimetry. You try to confuse forest and urban areas. Okay, the way to differentiate between them, maybe as Laurent explained you yesterday, is to use polarimetric SAR interferometry, and Costas will show you in the next day tomorrow. The way to differentiate between urban and forest is through PolSAR, through height. Okay. Here is a composition which is completely different. Someone could argue that it's super green, the forest, and this is the drawback of the Freeman decomposition. It overestimates the presence of volume. I mean, it's a limitation, but this decomposition was established in '92. So for that time, it was breakthrough, okay? Because it started the physical interpretation. Okay? You have other ones, the Yamaguchi decomposition in 2005. You make the same rule, you decompose in different canonical scattering mechanisms. Okay, and here you have, I wanted to give an explanation that I discussed with Dr. John Sengley. I mean, all the sequel of decomposition that have followed this physical-based decomposition, where you impose some kind of canonical physical mechanisms. Okay, you can go from 2, from 3. I mean, all the decompositions that go above 3, the elements are not orthogonal. They have some type of correlation, because you can estimate up to 3 independent scattering mechanisms. If you increase the number, they will be somehow dependent. Okay, which is very useful because you introduce more physical interpretation. Okay. Many of the decompositions try to tackle the problem of negative power that is originally from the Freeman decomposition. So they use different type of alternatives, orientational compensation. All of them try to attack the problem of HP, the estimation of HP. Okay, so Johnson Lee, what they did is to tackle the problem of the rotation invariance, to try to estimate HB. Okay, Yamaguchi in 2005 introduced more elements to try to overcome this overestimation. And finally, Jacob Van Zyl came in 2009 and 2010 with a very elegant solution that basically imposed, or it's an algorithm that avoids the introduction of negative powers. And the result is that they do not overestimate the volume. Okay? I mean, estimation of the volume is super complex, okay? Because it goes to electromagnetics, the multiple bounds, etc. Okay? Here you have the result of the Yamaguchi decomposition. Okay? And then we go to the second family of target decomposition theorems, which is eigenvalue, eigenvector decomposition, cloud quantity decomposition. It has many names, okay? But basically, the idea, and the most stupid idea, is something super stupid. Before that decomposition, the polarimetry was always considered in terms of the scattering matrix. Only a scattering matrix, 4 by 4. The idea that Shane Cloud had, you will see super stupid, is to transform this scattering matrix into a vector. And when you transform that into a vector, you can define the covariance matrix. From the scattering matrix, you cannot define you cannot obtain the scalar product, the vectorial product between the two vectors to obtain the covariance matrix. I mean, it's a super stupid idea, but it's super important because it opens the door to all this interpretation. Okay? So basically, what you have in here is that you have the scattering matrix in a vector form in the Pauli form. Okay? HH plus BB, HH minus BB, HB. And as a vector, you can have this product in here. With a matrix, you are not able to define that product. Okay? So therefore, we define the matrix T. Whenever you have a matrix, you can decompose the matrix into these eigenvalues and eigenvectors. Okay? Which is this decomposition. It's super easy to do. Okay? You have on the left, on to the right, the U matrix that contains the U vectors, which each vector corresponds a rank 1 scattering mechanism. So each single vector U1, U2, U3 corresponds to a scattering vector, and lambda 1 corresponds to the power of each element. So we are able to decompose the T matrix in the combination of these U vectors. The problem is that these U vectors do not have a straightforward physical interpretation because it's just mathematical. Okay, what we can do? We can parameterize these target vectors. Later on the lab sessions, you will have to do that interpretation. So U1, U2, U3, target 1, target 2, target 3 correspond the basis in which we decompose this matrix. So the physical interpretation will come from the interpretation of alpha 1, alpha 2, and alpha 3. Okay? And the power represents the strength of each one of these mechanisms. So we will have the physical interpretation from the interpretation of alpha 1, alpha 2, alpha 3, and the strength will come from lambda 1, lambda 2, lambda 3. Okay? So therefore, our decomposition is like this. Okay? We define T matrix as lambda 1, U1 complex conjugate, lambda 2, lambda 3. Okay. In order to go forward with these decompositions, we will define the probabilities of each scattering mechanisms, which basically is as given in here, Py, which corresponds to lambda y divided by the addition of the 3 lambdas, which correspond to the span, the total power. So we define the relative power of each mechanism to the total power, which defines the probability. So therefore, in order to characterize the average mechanism, what we can make is to weight alpha 1, alpha 2, alpha 3, or all the parameters that characterize the mechanisms by the probability. So therefore, we obtain the mean scattering mechanism. Okay, so therefore we will have alpha 1, alpha 2, alpha 3, which define the single scattering mechanisms, and we define the average mechanism with the mean alpha angle, which characterize the mean physical behavior of the average target. Okay, so therefore we have the mean dominant scattering mechanism, which characterizes the data. So therefore we are able to characterize completely the polarimetric behavior of the data. Okay, here you have a Pauli decomposition combining the mechanisms. Okay, and as you can see, you obtain something pretty similar. As I said before, you don't expect to obtain something radically different because all of them are describing the thing. In here, of course, we are wisely choosing the colors because the first normally refers to the single bounds, in red double bounds, in green the volume. Okay. Okay, so let's go to the physical interpretation. How do we interpret these alpha mechanisms to obtain that? In the case of the volume, okay, on the eigenvectors, we start with the same physical analysis as we did with the Freeman decomposition. Okay, we start with a cloud of needles that randomly oriented, and we end up with a T matrix of this form in here. Okay. If we go analyze azimuthal symmetry scatter, which is, I explained it before, we play with the different alphas, okay, and we end up with this physical interpretation, okay, which is the important thing. When we are in a case where the mean alpha angle is equal to 0 or close to 0, that means that we are in the case of bare surfaces. Okay? In the case alpha is close to p/2, 90 degrees, the model gives us the information that we are in front of double bounds. And whenever, or wherever, sorry, or whenever, alpha mean is p/4, we are in front of volume scattering. So this is the physical interpretation of the U mechanisms which are obtained mathematically. There is a problem, and I will show later on. What happens if creating this alpha in here, probability 2 and probability 3 are very low. In those cases, if probability 2 and probability 3 are very low, we are introducing noise into the mean alpha. So many times, okay, in situation in which we have one scattering mechanisms, we equal mean alpha angle to alpha 1 in order to avoid the introduction of noise. Okay, this is not a trick thing we do in order to better estimate the data. Okay. So we have the interpretation of the alpha, So we have introduced a physical interpretation of the mathematical decomposition. We can even go further and define new parameters from the decomposition, which maybe for some of you is the well-known parameters entropy and anisotropy. So the entropy in the von Neumann sense basically give us idea of disorder. So basically the entropy we calculate into that with that expression, and in the case of pure target, then one scattering mechanism is whenever H is close or equal to 0. And when H is close to 1, lambda 1, lambda 2, lambda 3 are equal, so it means entropy equal to 1. And anisotropy is defined as the relative difference of the second to the third eigenvalue. And normally, we only use anisotropy whenever h is larger than 0.7. Okay? The information that is giving us entropy is that the usefulness of polarimetry. The closer we are to 0, the more useful is polarimetry. The closer we are to 1, the less useful is polarimetry. That's why, in the case of forests, where you have high entropy, polarimetry more or less is useless. This is why we need to go to polarimetric SAR interferometry. As Costas will show later on, we introduce interferometric information in order to decrease entropy, to give more information to polarimetry. Okay, so therefore we have transformed the original eigenvalue, eigenvector decomposition in terms of new parameters, which is the entropy, the anisotropy, the alpha decomposition. Okay, this is the relation between the mathematics and the physics. Let's go to see one example. No, I will finish with this, 5 minutes. Okay. I want to give you this because on the practical session, we will go into the details of this, okay? Just before to finish, you have on the slides, at the end, there are more cases, okay? There is no relatively new information. There are more cases where I analyze the entropy and anisotropy. There is the case of one forest, the case of one bridge, which is super nice because you will see everything. And then polarimetric orientation angle, which is a tricky thing where you can obtain topography from polarimetry. Okay, so you have the slides. So take a look to them, send me an email in case you have questions, okay? But normally I'm very slow giving presentations, so I prefer to be much more clear into giving the information. That my goal is not to finish the whole presentation, okay? To run, okay? To run, it's not useful, okay? So let's go to analyze this imaging here. So the entropy, as you can see, in the forest is equal to 1. Okay? And if you go to alpha, you could see that alpha is 45, green. Okay? If we go to the urban area, which is on the middle to the right, if we go to the alpha, you will see that in that area you have a lot of red, which means double bounce. Okay? Entropy is very low in this cornfield. Okay? Which is an agricultural field. And if you go to entropy, you will see that you have this collection of 5 dots that correspond to the corner reflectors. Corner reflectors, remember, it's diagonal. It's magic 1, 0, 0, 1. So that means alpha equal to 0. Okay, and if you go to that image in here, you will see that they are entropy 0. So you can detect from this image the presence of point targets. Okay, you will see a lot of point targets into the urban area. Yes, because they are super strong canonical scattering mechanisms. Okay. Here, just to close, I will give you one example. Here is close to the DLR. You have some urban areas, some forest. Here you have the entropy, okay, super clear, where you have forest in red. And I want to go here This is L1. So you see volume and double bounce in the case of the forest because you have penetration. And you have in here and in there, you have some farms, some little urban areas, and you can identify them through the presence of double bounce scattering mechanisms. Okay? Questions? Regrets?
I think it was slide 6. You said that there was a fourth term that we didn't use, and it was
yeah.
What does it represent and why?
Normally, when we use SAR sensors, transmitter or receiver are at the same position. It's monostatic case. So in that case, HV is equal to BH. In the case of B static case, where the transmitter and receiver are in different positions, they are no longer equal. So that's why it introduced the fourth parameter. I mean, all the systems that are now in place are all of them monostatic. The only system which is B-static is the new Harmony mission Earth Explorer, which will come in a few years, okay, which is a bi-static system. Basically, you will have some small satellites following Sentinel-1. So transmitter and receiver will be at different positions. Any other question? So if not, in the lunch or afterwards, I'll be happy to answer your question.
The local versions of decompositions, do you have experience with that? Can you comment on what you can use local versions instead of platform,
So, well, can you repeat your question? Because okay, yeah, of course, you lose one channel. Polarimetry is something that is all or nothing. Okay, either you have full polarimetry, and whatever is not full polarimetry, you cannot do all this. I mean, you lose a lot not having that. For instance, in the case of Sentinel, I think your question is related to that. The problem is that the correlation between, due to the reflection symmetry, the correlation between HV and BB is 0. So therefore, you have a pseudo covariance matrix 2 by 2, which is essentially on distributed target diagonal matrix. So that's why whenever you play with polarimetry with Sentinel, you end up playing with the amplitude or the ratios between the two images. You don't go really farther into that because you don't have fully polarimetric data. There are a lot of limitations with dual pole, strong ones, I would say. For instance, you have SAOCOM, which is a current system that works with fully polarimetric data. You have RadarSat-2, which is a powerful machine. I mean, this is an astonishing machine. It was the best polarimetric system in the space, I have to admit. And ALOS also has fully polarimetric data, where you can play with all this. The future system, NISAR, will be fully polarimetric. As far as I know, they will fly fully polarimetric only on the US. Yesterday, I was informed that Sentinel-1 maybe will have fully polarimetric data, but not in operational mode. So that's a limitation. Basically, at the end, the main limitation of polarimetry is that when you have a polarimetric system, your swath has half of the original swath. So you compromise revisit time. So there is a fight between either you have polarimetry or you have longer revisit time. Okay, that's the main thing. Okay, and people, they don't want to lose revisit time for polarimetry at the moment. Okay. Okay, so let's close here and let's go to lunch.
Yesterday, we showed the practical, simple course, but before.